because we are using the symbol NA always for the right null space. For fundamental subspaces, for A belonging to R, M by N, R. What does it mean? A belongs to R, M by N, R.
Matrix M by N with rank R.
R. It's a matrix of M by N, M rows, N columns, and the rank is R. What can we say about R in general? Do we know what is the value of R? Right? We had it before when we were talking about the rank. Row space, column space. The rank is R. Okay, the rank is R. So it means that from R I go to R here, because this is how the meaning of R is. If R of them are in the row space, what is the meaning of rank?
The number of
Linearly independent. In other words, when we put this one, it means that there are some of the rows, columns which are linearly depending on each other, right? So if we have the independent ones here, what are the number in here? N minus 1, N minus R. Similarly, it is N minus R in here. N minus R in here. This is Rn. This is Rn, the whole part. Let's start with the easy one. This is our linear transformation R. Can you tell me that what is here? What is this is called? RA, isn't it? What was the definition of RA? Is from here, our linear transformation are taking us to range of A, right? And what we have in here, what can we say about this? Maybe I can help you in this form. What is this?
The null space.
Is excellent, null space. So if this is null space, which goes to 0, this is the definition of the null space, and this is RA, okay, what can I write in here from the whole terms, things that we have seen? If something is in here, can it be in NA? I. If there is something in here, can it be in here?
Yeah.
No. we can see that they are very disjoint. If something is in here, it cannot go to 0. Because if it wanted to go to 0, it will be in a null space. Look, what is a null space? Null space is that those elements in here, which A will take them to 0. What is in here is those elements that are taking, A is taking us to the RA, not to the 0. Because if it takes it to the 0, it will be NA. So can you tell me that what is this one called, if this is NA? Because if something is in here, it's not in here. We have just learned that it's null space A orthogonal complement. Well, if this is the case, can you tell me now what is the last one which is left? You know that the vector in here cannot be in here, because if they were in here, they would be in here. They would not be in here. It's range A complement, orthogonal complement. However, orthogonal complement calculation, not very easy. I can represent these two in an easier form. Can you tell me that what is an easier form to represent NA orthogonal complement? Number 1.
Yeah, range A transpose.
This is the range of A transpose, and this one is null space of A transpose, null space of A transpose. This is still an important image. Assume A belongs to R 4 by 3 with rank 3. Okay? 4 by 3 with rank 3. 4 by 3. Can you tell me that how many vectors I will have in RA transpose, or let's make it even easier. How many vectors I will have in NA? And what will it be its dimension? You might want to look the last example that I solved in here for this example of spanning, to calculate the null space, to calculate the orthogonal complement. We understand that these two are orthogonal complement of each other, right? Mm-hmm. So in other words, if I have all my vectors in here, I will have nothing here, because then they cannot be orthogonal to each other. But if some in here, some will be here. How many are in here?
3.
I already know. I have 3 vectors in here. And how many vectors will be in here?
You have 1 probably.
1. So how many vectors do I have? 4. So there are 4 vectors. Which 3 of them are in here. 1 of them is in here. What is the number of elements in each vector?
4.
4 by 1. Right? It's 4 by 1. Now I take it to the other side. So how many vectors I will have in here? 3. So what can you tell me about the size of these vectors?
Four times m?
Are you sure?
No.
all the rows will start to go to the columns, right? Column space. How many columns do I have?
3.
3. So it will be 3 by 1, 3 by 1, 3 by 1. But let's do a numerical example. But before doing a numerical example, we need to know a few more definitions. Given that then every vector v in the can be written in a unique way as what do we call Rn? Do you remember?
Domain.
Yeah, very good. I mean, in the exam, you don't have this type of filling the blank. It's just like I want you to think and remember. V is equal to x plus y, where x belongs to NA and y belongs to NA orthogonal, which is, we know, R A transpose. So any vector that I have, in other words, my Rn, look at here for a second, please. Any element in Rn is either in here or in here, right? So we can write it in this form, that Rn is basically Na direct sum Ra transpose, which we could write it as actually Na direct sum Similarly, we can write every vector W in the Rm can be written in a unique way as what should I put in this empty space?
Codomain.
Codomain. W is equal to x plus y, where x belongs to Ra and y belongs to Ra orthogonal complement, which is Na transpose. We know that this is the left null space of A, and this means that the Rm is Ra plus direct sum of Na transpose. Now that we know these terms, we want to redefine some of the old school terms that we knew and see that how they are being actually linked with each other. And it is important because later we want to use them in the next chapters in order to find some of the properties and terms. Let A be from V to W, vector spaces, be a linear transformation, right? Be a linear transformation. Then A, number one, A is onto, or we call it epic, or we call it surjunction. Injective. The other one's injective. Surjective. If. Now, before I write what is the condition, let's get back to, again, calculus 1 or even high school mathematics. And let's remember, what is onto?
Mapping from one space to the other one.
In the functions that we have, how do we call it something is onto? If we call something is onto, if from the domain, we can cover all the code domain. In other words, whatever we have in the domain will be mapped definitely in all code domains. Definitely in all the code domains. So in other words, so this was the definition that we had. Can you tell me that, how can I represent it from all these notations that we have? So onto means that I am mapping whatever I have into all the code domains. How do we represent mapping to concept? What is the notation that we use in order to show the sets which have been mapped to? This RA, range A, tell us what is the set that we have mapped to. It shows the result of the mapping, right? Now, onto means that we have to have the whole code domain in here. So it's onto if RA is equal to the whole my code domain. The whole my code domain. What can we say about null space in here? Do we have elements in the null space? We have probably we do. It depends to check some other stuff. Now the second thing is, we had onto, what was the other thing that we had? Do you remember? For the functions, we were calling a function is onto, or the function is, we had one more term. One-to-one, have you heard of one-to-one? The functions can be one-to-one, can be onto. So A is 1-to-1, or we show it as this, or we call it monic. This one was surjective, this one is injective. If now, before we talk about this, do you remember why we wanted to have things to be one-to-one? What was properties of the one-to-one? Do you remember, Hassan?
I think it's about having unique values for.
Yes, that's true. But I mean, there was one-to-one in the function means that for every x we have only one y. It's not that one x can go to two y's. But we have something very specific. I mean, if the functions were one-to-one, then something was existed. Well, what was the problem if the function is only onto? What if the function is only onto? This means that we might have two different values of x which result into the same y, like y is equal to x squared. X is 2, we get 4. X is minus 2, we get 4, right? So what is the problem in here? If I tell you that y is 4, you don't know which x you have to go. Whereas in the one-to-one, we said that, as Hassan said, we have unique way of connection. For this x, you have only this y. It's not possible to have another x which results in the same y. So then it means that if I, for example, y is equal to x cubed. If you give x minus 1, you get y minus 1. If you give x 1, you get 1. So if I tell you that y is minus 1, what is the value of x? Minus 1. What is this operation? That I give you the value of y and you tell me the value of x?
The inverse function.
Yes, then the inverse of the function exists. You can calculate the inverse because it's a uniform one. Now, in order to have the inverse of the function, we have, or the sets, we need to have one condition. And the condition is null space of A is equal to 0. Null space of A is equal to 0. Why?
If it's different from 0, then more solution will exist. It can contain 0,
Exactly.
but if we
Look,
have more.
you remember we had this shape that we draw, and we said that this is the null space. In the one-to-one, we said that for one element, I should have only one other element. I cannot have two elements going to one, otherwise it's not one-to-one. If the null space is not 0, then it means that I have vector x1 and vector x2, which both of them are going to the one value, so it cannot be one-to-one. So it cannot be one-to-one. So this is, I mean, this is how you have to be able to visualize it. If this is not 0, it means that we have, let's say, at least two elements, that these two elements go to one y. So if I tell you that y is 0, you don't know if you have to go to x1 or x2. So what happens is, then in order to make it one-to-one, the null space must be 0. it, Ike? Two equivalent characterization of being one-to-one are, well, actually being one-to-one, we can represent it into two forms also.
Sorry, I have a question. Actually, it's concerning the diagram you had drawn before, the four fundamental subspaces. The column space, what's the dimension of column space? R?
N, it depends. If this one was Rm, then the other one is Rn. If this is Rn, this one is Rm. How we want to write it down?
Okay, but we had defined A as a...
Well, we said that this is M by N, so this is the M by N, then this is M, this is N.
So, but that is a column space, so how does that translate? And we had defined that we had 3 by 1 for the column space.
We have 3 by 1, it
If
means
we have
that...
the A to be 4 by 3, yeah. So the column space becomes 3 by 1.
Hang on, what they wrote, we had R 4 by 3,
Yeah.
which means that we have 4 columns. No, we have 3 columns.
Yes.
So we have 3 columns. So what is the problem?
Now the dimension of each of them was...
Each
3
of
by-
the vectors of this one belongs to R4. We have 3 columns which are in R4.
You had written each of them is 3 by 1.
Did I?
Yes.
So it has to be 4 by 1. Then the other one should be 3 by 1.
Yeah. That's...
Okay. So can we come back to this one? So we will get back to this one and then correct it. I will check what I've written. Now the two way of representing is A. If AV1 is equal to AV2, then V1 is equal to V2. This is also a representation for one-to-one. If V1 is not equal to V2, then a V1 is not equal to a V2. I mean, in some books they are using this type of notation. We will do one numerical example regarding to that diagrams, and we will fix it while we are doing that numerical example. So one-to-one means that all the elements that we have in our domains will be connected to the unique elements in the codomains. In other words, we don't have any elements in the codomains which has been achieved from 2 elements that we had in the domain. In other words, the inverse is existing for us. Whereas in the onto, we don't have any restriction regarding to that 1 element or 2 elements going to something in the codomain. The only thing that we had in the domain in the onto is that all elements in the codomains have been covered. Now, can something be onto and one-to-one? Can something be not onto and not one-to-one? In other words, can you find a function that is not onto and is not one-to-one? And not onto means that you define your codomain, and there are some values of codomain which are not being touched at all. Y is equal to x squared. Is it onto? If we consider from vector space R to R.
It's not,
It's not. Why it's not?
because it doesn't cover all the values.
Because it doesn't cover all the values. The negative values in the codomain are not being touched at all. So, but what about one-to-one? Is it one-to-one?
No,
No. Why?
because we have two values for x corresponding.
Exactly. X1 is not equal to x2 in case of 2 and minus 2, but x squares, I mean, the results are the same. So we can have a scenario which is not one-to-one, which is not onto. We have examples which is onto and one-to-one. Can I give you an example of onto and one-to-one? The word easiest function ever. Y is equal to x. This is onto, this is one-to-one, and we know that the inverse also exists. Do you remember how we could understand from function perspective if a function is onto or one-to-one? We had something to do. Like if this is a function that we have, how can I understand that this is onto or this is one-to-one? Onto means that if we draw any line parallel to x-axis, onto means that it has to cut at least at one point. It has to cut at least at one point. And one-to-one means that if I draw this line, it has to cut it at most at one point. So it is onto and one-to-one if it is cutting it exactly at one point. Right? Exactly at one point. Now,
What do you mean at most? Cutting?
at most is this. Is this function onto? We say yes because at least it cuts at one point. Here it cuts at 2 points, 3 points. At most means either it doesn't cut it, or if it cuts, it cut at most at one point. Right? So, but we understand that we are not talking about more general form, we are talking about vector spaces, and we see it from vector space point of view, but these are some things that maybe you have seen them in your calculus before, like how we could find it, it's 1, 2, or not. In the calculus, we actually were using this one quite frequently. We said that it is one-to-one if fx1 is equal to fx2, then we get to the conclusion that x1 is equal to x2. Or we were saying that if x1 is not equal to x2, we came to the conclusion that fx1 is not equal to fx2. Right? We had them in the undergraduate calculus, or maybe even in the high school. Do you have any question? we will talk, we stop here, but in the next lecture we will talk, before I do the numerical example, we will talk about how the dimensionality will be changed in that graphic, and then we will go over the example, and if I had a mistake in that example, we will fix it when we have the formula for the dimensionalities. Okay? Okay, if you have no question, this is the end of the lecture for today. And on, can I stop it? On Friday,